In this video, I'm going to be showing you guys how to build a command line version of Minesweeper that looks something like this. We're going to be using recursion and classes to build our game. Now, before we get started, I just wanted to say that I'm building a very bare bones command line version of this game because I believe that when you're learning how to code, if you actually want to learn how to translate your ideas and algorithms into Python, the bulk of that is going to be in actually implementing the game, not figuring out how the UI works. I think that the UI, while it's important, it is somewhat secondary to actually learning the coding process and the algorithmic process that's involved with building these games. Let's start off by defining the play function. So here, our goal of this function is to play the game. So we're going to define play, pass in a dimension size, which is going to be the size of the board, and the number of bombs on the board. All right, so in step one, we're going to create the board and plant the bombs. In step two, we're going to show the user the board and ask them where they want to go. And now step three, well, if the location is a bomb, then we show the game over message because they just dug where there was a bomb But if the location is not a bomb, then we dig recursively until each square is at least next to a bomb, right? So you think about how Minesweeper works. If you dig somewhere and it's empty and everything around it is empty, then you keep digging until you get to a number. And that number represents that that square is next to a bomb. And then in step four, we repeat steps 2 and 3 until there are no more places to dig. And then we've achieved victory. All right, so right now we're just gonna say pass because we'll get back to this function. Okay, so let's take advantage of our object-oriented programming tools that we have in Python, and let's create a board object to represent the Minesweeper game. So this is where we can say, create a new object, or dig here, or render this game for this object. Let's define a class called board. And here, we're gonna initialize it with the dimension size and the number of boards. So let's keep track of these parameters because they're going to be helpful later on. So let's assign self.dimension size, dim size, to the dimension size that was passed in, and then self.number of bombs to the number of bombs that was passed in. And then we're going to create the board, but let's get back to that. And at the very end, we're going to initialize a set to keep track of which locations we've uncovered, which locations we've dug in, where the user has gone. So self.dug is going to be an empty set. Okay, and then let's create the board. So let's actually use a helper function. So self.board equals self.makeNewBoards. And here we're going to plant the bombs too. So let's define that. All right, so we're going to define make new board, pass in self, and basically this is going to construct a new board based on the dimension size and the number of bombs that we pass in. And there are a bunch of different representations that we can use. That can be like a list of lists where each sublist is just a row of this board. So here we're going to generate a new board. This board is going to equal, it's going to be none, and then repeat that dimension size number of times because that's how long we want this list to be. And then we're going to have dimension size number of these lists so that we can get a square board. And so this creates an array that looks something like this. It's just going to be a board where it's none, 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 etc. for our whatever dimension size that we define it. So then next we have to plant the bombs. So here we're going to say bombs planted equals 0. We're just going to use a while loop. And we can say while bombs planted is less than self.number of bombs, we can pick a random location for the bomb, right? So let's actually go up here and let's import random. And now for the location, we're going to do random.randint and somewhere between 0 and self.dimension size squared minus 1. And so you can think about this logic as like, we're literally assigning a number from 0 to the number of spots on the board, and we're assigning each spot on the board its own unique ID. And then this random.randin is returning a random integer n such that it's between the bounds a and b. So a would be 0, b would be the largest ID in that list. And then here we want to actually get the row and the column of that ID that we've chosen from this random selector. So we're going to do the location and then this / self.dim size. And what this is going to do, it's going to say how many times does my dimension size go into whatever location that I've chosen. That's going to be the row that we're indexing in. And then now, once we have the row, how do we know which column? We have to divide by the dimension size, and then whatever index is left over, that's going to be how far into that list we have to index in order to find the column. So once we have the row index and the column index, we can index into the board, and then we can say if board and then row column, we're going to index into that specific row column location on the board. If it equals a bomb, so this star is what we're going to use to represent the bombs, then this means that we've actually planted a bomb there already. So we're not going to increase bombs planted, right? Instead, we're just going to keep going. And this is actually the reason why I'm using a while loop and not a for loop. Because in a for loop, every single time we skip or continue, we're still counting that as an iteration. But here, I only want to increment when I actually get something that's not a bomb yet, and then I plant the bomb. So yeah, that's why I'm using a counter, and that's why I'm saying, hey, check if this is a bomb. If it is, keep going. If not, then we're actually going to plant the bomb, and then we're going to increment this counter bombs planted. And then at the very end, I'm going to return the board. All right, so that is making our new board. We're going to plant the bombs right there. All right, so what other information is useful? Well, we want to know at each spot on this board how many bombs are around that spot. That's going to help us when we choose where to actually dig, right? When the user inputs something, well, how do we know where, whether or not we should keep digging around it? And yes, we can implement a check at each point where we say oh, if we dig here, we're going to check all its neighbors, and then we're going to dig again, and so on. But we could also just assign values to every single space on the board that represents how many bombs are in the neighboring spaces. So let's call that assign values to board. So here, let's define assign values to board and pass in self. All right, so now that we have the bombs planted, we're assigning a number 0 through 8 for all the empty spaces that don't have bombs, and this is basically representing how many neighboring bombs are there. We can pre-compute these, and it'll save some effort checking what's around that square later on. Basically, we want to check every row and every column. So for R in range, self.dimension size. For C in range, self.dimension size. This is going to be the row index and the column index. So if the item at the board, if at those indices on the board, it's a bomb, we're going to continue, right? Because we don't want to actually override any of the bombs that we've planted. But if it's not, then we pass this if statement, and then we say, okay, for this location on the board, let's create a new function called getNumNeighboringBombs, pass in the row index and the column index, and then this function is going to give us the number of bombs that is surrounding that row, column. All right, so let's define this. Define get number of neighboring bombs. We're passing in the row and the column. If you're confused of why I have R, C up top and then row, col, these are just variable names. You just have to make sure that they match where you're actually calling them. So for example, when I call the function, I'm passing in R, C because I've defined R and I've defined C in my for loop. So those are variables that I've defined. And now when I create this new function, I can call the parameters that get passed in whatever I want, right? And so here the R would correspond to the row and the C would correspond to the column. So now let's iterate through each of the neighboring positions and sum up the number of bombs. So here I've kind of imported a list of all of the neighboring positions. You can see that top left is row -1, column -1, and top middle is row -1, column, and so on. And so we're going to check all of these. And we have to make sure that we don't go out of bounds. So that's just a little reminder. Okay, so first we're going to initialize the number of neighboring bombs just to a variable, set it to 0. This is going to be our counter. And then we're going to say for r in range, row -1, row +1. And then keep in mind that due to the nature of the range function in Python, we have to add a +1 to the end. And then same thing for the column. For C in range, column -1, column +1, +1. That should be a plus. All right, so basically what we're doing here is for the current row that we're at, we're checking below and above. And then for the current column, we're checking to the left and to the right. And so when we sum up all of these combinations, we get every little piece of the 3x3 grid. And then we can say if r equals the current row that we've passed in, and if c equals col, the column that we've passed in. This is basically saying, like, this is our original location. We don't actually have to check this. So we continue. But if it's not, if self.board at rc equals a star, so that means that there is a bomb at that location, that means that we have a neighboring bomb, right? And so we can increment number of neighboring bombs by 1. And then at the very end, after we've gone through all the neighbors, we're just going to return the total number of neighboring bombs. Now we have to go back up here and we have to make sure that we don't actually go out of bounds, right? Because what if row is at 0? What if we're checking the first row? Row -1 is going to be -1. That's out of bounds. Here we're going to add a max statement just to make sure that, row -1, if it ever goes past -1, we're going to take 0 every single time we go below that 0 bound. And then for the upper bound, we're going to do the same thing. We're going to take the min of row +1 and then self.dimension size -1, because that is the maximum index that we can go, right? And then of course we're going to use the exact same logic for the columns, just like this. Solve some spacing stuff. And so yeah, now we've got our bounds checking and we can return the number of neighboring bombs. All right, let's go back to our play function now. So step 1 is creating the board and planting the bombs. So what we can do is we can say the board equals an instance of this board class, and then we're going to pass in the dimension size and the number of bombs that we've passed into this play function. And this is going to automatically, go through that initialization function, and it's going to initialize the board and plant the bombs and create an empty set for Doug and so on. All right, so now part 2, we're going to show the user the board and ask where they want to dig. And then we're going to check if the location is a bomb, is not a bomb. We're going to dig recursively. So let's actually go back and let's implement some of these functions so that we have them, handy when we need them. So let's define a function called dig within the board class. And we can dig at a certain row and column index. So we're digging at whatever location the user has specified. And let's return true if it's a successful dig, and then a false if we've actually dug a bomb, it's game over and we've lost. So there are a few scenarios here, right? Either, we can dig somewhere and we hit a bomb and then it's game over. We can dig at a location with neighboring bombs and then, we finish the dig because we've uncovered a number that's not 0. But we might also be digging at a spot where there are no neighboring bombs. And in that case, we want to dig its neighbors until we actually get somewhere where there are neighboring bombs. So the first thing that we want to do when we dig at a row, column, is we want to add a tuple to self.dug to make sure that we're keeping track of where we've actually dug. And then we're going to check the board at that row and column. So in our first scenario, if it's a bomb, we return false if there's a bomb dug. Now, if we check that space and it's a number that's greater than 0, that means that we've dug at a location with neighboring bombs and we finished the dig. So we just return true because we did not dig a bomb. So now if at that row and column on the board, it's not a bomb, it's not a number greater than 0, it means that that spot is equal to 0, right? So here we're going to use the same logic from get number of neighboring bombs where we're checking for the neighbors. And let's paste that down here. So here we're going to check R and C for all the neighbors. And so if R comma C is in self.dug, then we continue. Because this is basically saying, don't dig where you've already dug. That's pointless, right? But after that, if it's not, then we dig at that location. So we pass in R comma C into this dig function again. And we continue through all of this. There shouldn't be a way where we ever get to a bomb, right? Because we should always be stopping at some square right before a bomb. So at the very end, we're going to return true. So I'm just going to add one more thing to this Minesweeper game. This underscore string underscore. And so this is a magic function where if you call print on this board, it's gonna print out whatever this string function returns. And so here what we're gonna wanna do is we're gonna want to return a string that shows the board to the player. And I'm gonna go over part of this function, but part of it was kind of just like if you inspect the code, you'll be able to tell what we're kind of doing. Okay, so first we're gonna create a new array that represents what the user should see. So let's call this visible board. So visible board is going to be, well, first let's just create an empty board just as we did above. So that's gonna be our list and list, and it's gonna be a sublist of size, dimension size, and we're gonna have dimension size number of those lists. So now for every single row and for every single column, we're gonna use this for loop again. If that row comma column is in self.dug, that means the user has dug at that spot. So visible board at that row and that column is going to be whatever the actual board value is. But if it's not dug already, then this is actually just going to be a space because the user shouldn't be able to see what's at that location yet. They haven't dug there. And we're going to put this entire board representation in a string. Now, what you can do is you can just honestly return like a string.join and then just this visible board. In this code, I'm going to make it a little bit cleaner. And this is all that this stuff here is doing. It's just some formatting code. You can look through it if you want, but I'm just telling you right now that it's just completely formatting to make it look prettier and to make it print out nice. And honestly, I believe that knowing how to implement Minesweeper is a lot more important to learn than learning how to print out a representation of the game. Okay, so now if we look at steps 2, 3, and 4, well, step 4 is basically repeating steps 2 and 3 until there are no more places to dig. So that kind of sounds like a while loop to me, right? And here what we're gonna do is we're gonna say, well, while the length of board.dug, so all the places that you've dug, remember that this is a set, so there are no duplicates. While the length of this set is less than the board.dimension size squared, because that's how many spaces total there are on the board, minus number of bombs, then we're going to allow the user to play because it means that they still have empty spaces on the board where they can dig that are not bombs. So the first thing we're going to do is we're going to print the board. And we're going to ask the user, where would you like to dig? And we're going to input this as row comma call, so something like 0 comma 3. And now here I'm going to use a regex split. So that's what re.split is. It's saying input where would you like to dig. This is going to return a string, and we're going to split that string by this regex. And so this comma is going to say, okay, detect any commas, and then this parentheses //s. Well, this is saying any white space, so any spaces that you see, and the star at the end is going to say 0 or more of those. So essentially this is saying match any part of this string that matches, just a comma or a comma space or a comma space space, whatever the user types, we're going to split that. So then we can handle something like 0 comma 0, 0 comma space 0, or 0 comma space 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 0, right? And here we have to import re, so let's go back to the top and import re so that we can split our string. Okay, so now that we've split our input, we now know what row and column the user is trying to dig. So we can assign row and column to the user input at 0 and the user input at -1. The reason why we use -1 is sometimes it's re.split, it has some fluff on the inside of this list. And so if we know that the row and the column are at the beginning and the end, then why not just take the first and the last item in this list? And I'm going to use int because we want these to be integers. So now let's do some bounds checking. If row is either less than 0 or greater than board.dimension size, or if column is less than 0, greater than or equal to the dimension size, we're out of bounds. So here we're going to print invalid location, try again. And we're going to continue so that we repeat this loop over again until the user inputs a valid row and column. But if the user did input something valid, then we dig at that location. So we can call board.dig at row, call. And so now we've already implemented this part, so we don't have to actually worry about the mechanisms of actually digging. We know that board.dig is going to return true if we've dug successfully and false if not. And so we can assign a variable called safe, whether or not our dig was safe. So whether or not we've uncovered a bomb or not, right? So at the very beginning, we're actually going to say safe is true because at the very beginning, we haven't dug anything. You know, we're safe. We have all of our lives. And so if not safe anymore, well, this means that we've dug a bomb and that's bad. We're gonna call break because this means game over. We shouldn't be continuing this loop anymore. We shouldn't be allowing the user to dig. So we're gonna break out of that while loop. And now at the very end, there's two ways to exit this while loop, right? Either you've won and there's no more spaces on the board where you can dig, or you've dug a bomb, nothing's safe anymore, and yeah, rip. So let's check which one. If we're still safe, this means that we've just run out of spaces to dig. We've dug every single possible spot to dig, and so we've actually won. Let's print congratulations, you are victorious. All right, but on the other hand, if we're not safe, that means that we've dug a bomb, and we can print sorry, game over. And here we can actually reveal the whole board. So we're going to assign board.dug to every single possible value of r, c on this board. So this double for loop in this list comprehension here is just saying take every single possible r, c value of this board and put it in this list. At the very end, we're going to print the board. And so this is going to reveal every single possible spot. Now let's call the play function to actually play the game. And we're going to put this in a name equals main if statement because this is just good practice. It's basically saying, like, if you have a massive project but you only want to run this file, the stuff underneath name equals main will only run if you type in python3 minesweeper.py. If you have a bunch of imports from a bunch of other files, it's not going to run any of the code under name equals main in those files. You're only running what's under name equals main in that one file. All right, so let's play the game. First, let's dig at, 0, 0. So here you see that we've dug at 0, 0, it was 0. So that means that, there were no bombs nearby. And so we kept digging until, there were some bombs nearby. So for our next spot, let's just do 4, 6. And then let's try that bottom right corner, so 9, 9. And you'll see that this actually dug a lot. So it recursively dug everything that you see that's 0. It dug until it hit some spot that was not 0. And if we look at this spot right here, 3, 7, well, this is actually, very clearly a bomb, right? So let's dig there on purpose. So we dug at 3, 7, and it says, sorry, game over. And it actually reveals that, yes, this was a bomb. And this was the entire map of our game to begin with. There you have it, a command line version of Minesweeper. One really good practice in software engineering is organization. This is just like any other discipline too. But when you're working in a team or you're working on big projects, you want everything to be in one place so that you can work towards your goals as seamlessly as possible. And typically I do this using my notebooks, Google Drive, GitHub, and so on. However, recently I've discovered this product called Backlog. And Backlog, I honestly think is incredible. You have task management, you can keep track of bugs, you can keep wikis in the same place, and just work with the team super effectively. So in Backlog, I've been trialing this for a month or so. This is the homepage. So here you can see like there are a couple of issues that have been assigned to me. The neural net loss is not decreasing during training. I have my projects up here. There are updates over here. And so I can even like click on one of these. So this is my food recommender neural net project. And we can see like the status of all of our tasks. It's super easy to just type in an issue and add a new one. And here I can toggle, whether it's a task, a bug, a request, something else. I can go to like my board. I've used Asana before where I can keep track of tasks in Asana. And this is like a super similar interface where you have open issues in progress, resolved. You can have like a list of all of your tasks over here, for example. And I can go to their advanced search and look at all the stuff that you can search. Like, this is pretty cool. What I think is the best feature of Backlog is that it's everything in one place. And so for like driverless, for example, when we're working on a team, the team lead will spec out a lot of the project details in Google Drive and share that as a document with the team. And we'll communicate through Slack and keep track of things that we have to do in Slack. What I find really cool about Backlog is that just in the software itself, you have wikis, files, you can even integrate like GitHub repos. So every single time somebody pushes, it can integrate with this software and create any necessary alerts that you might want. The fact that Backlog has everything kind of integrated into one software is really awesome for keeping track of projects, because now I don't have to pull open GitHub for my code and Google Drive for the specs from 2 weeks ago and Asana for all the tasks that we still have to go through, and et cetera, et cetera. So you see my point, right? If we ever record a team meeting, we could easily come over here to files and we can add the files directly in the project as well. All in all, if you're trying to manage a team, I think that Backlog is a great way to have everything just organized in one place so that your team can work as efficiently as possible. And just a quick note, Backlog has a free trial for a month where you don't even have to enter your credit card. And so you can try like any of these tiers that have more features, or there's even a free tier where you can have 10 users, one project, and 100 megabytes of storage, and that will be free forever. So if you guys are building projects, if you guys want something that will keep track of where all the little pieces are, what like additional tasks you guys have to do, I think that Backlog is a great software that will really help your team stay organized and stay focused so that you guys can devote that energy towards whatever it is you're trying to achieve.